This video, we're going to talk about topic 7.5, approximating Euler's method. So our essential question is, how do I use Euler's method to approximate a particular solution to a differential equation? And our I can statement is, I can use Euler's method to approximate the particular solution to a differential equation. So Euler's method is a numerical approach to approximate the particular solution of the differential equation y prime equals f of xy that passes through the point y sub 0 or x sub 0, y sub 0. Really what's going on is we talked about slope fields the other day, and that because it's kind of an overall approximation. But if we want a tangent line approximation or approximate that's really right on the slope, right at a point on the curve, we can use this Euler's method in order to get that. And notice we've got a curve and we've got some approximations here. So, because sometimes we don't have all the information, but we've got some numbers to work with. There is a formula for it. It is very similar to a tangent line. Looks like a tangent line. Remember, a tangent line is y equals m times x minus x sub 1. Sorry, that's not it. Y minus y sub 1 equals m times x minus x sub 1, and then we can usually you could take that y to the other side, plus y sub 1. So it kind of looks like that a little bit. Or equation of a line, y equals mx plus b. So that's really what we're doing here, is finding this equation line. So it's y of x is approximately, because it is an approximation, so we use the approximately symbol, y of a plus f prime of a times dx. So y of a represents the previous y value. F prime of a, that's a derivative, so that's the slope. And then this is what we call the h, or the step size. So there's going to be a step in between each one of the approximations. And really, I mean, look at it. Y equals mx plus b. So it's really equation of a line. All right, so we're going to, example one, we're going to use the Euler's method at work. We're going to use Euler's method to approximate the particular solution of the differential equation y prime equals xy passing through the point 0, 1, and we're using a step size of 0.2. And I think I may have deleted some of the work. Oh, we're supposed to approximate. I totally deleted part of the problem. Approximate y of 0.8. So I know I'm starting at 0 and I have to get to 0.8. Okay. So I know that I'm going to rewrite this, and instead of writing y prime, I'm going to write it as dy dx equals xy. And I know I've got the point 0, 1 to start. Sometimes in calculus, we'll write a point like this, but sometimes we'll go back and write it like y of 0 equals 1, where you're showing the x value you're plugging in and the y value output. So this is where I'm starting. I know my step size is 0.2, so I know my next one that I'm going to approximate is for 0.2. I'm going to use the approximately symbol. So I'm going to apply this formula. I'm going back to my previous y value. My previous y value is 1, plus the derivative of the previous value. So if my at 1, my x value was 0. So my derivative of my previous, I'm going to plug into this. So I'd have 0 times 1, which is 0. And then I'm going to multiply by my step size, which is 0.2. And when I add that up and multiply that out, I get 1. So now I'm going to keep going until I get to what I wanted to approximate, which was 0.8. So y of next would be 0.4, because my step size in between, I am adding 0.2. So my previous y value is 1, so I'm taking my previous y value from here. Plus, now I take my new point, this, and I plug it into here. So I have 0.2 times 1, so that would be 0.2. And then I'm going to use my step size, which was the 0.2, right, from here, 0.2. And then when I multiply that and add that up, I get 1.04. I'm going to keep going until I hit 0.8. So I'm going to do, my next step would be y of 0.6 because I'm adding on a 0.2. I write down my previous y value. So this goes here. Okay, plus, then I take my previous, I'm going to take my new point, 0.4 and 1.4. So 0.4 times 1.4, that's the derivative. And when I multiply those two together, I get 0.416. And then I multiply by my step size of 0.2. When I multiply all that out, 1.1232. Almost there. And I wrote it equals. I should have written approximately. So y of 0.8 is approximately. So I go to my previous y value, 1.1232. So that was previous y value. I should have done it in the color. All right. Plus, then I multiply. Oh, not that. Excuse me. Multiply my previous y, or my point for my dy dx, right? I'm plugging into here. So I'd multiply together the 0.6 times 1.1232. When I do that, I get 0.67392. And then I have to multiply that by my step size of 0.2. When I add all that up and multiply, I end up with 1.25798. Remember, you have to be accurate to 3 decimal places, but you don't want to do any rounding in the middle. You want to leave all of these decimal places in the middle.